Most people picture the Big Bang as an explosion, a tiny point, a flash of light, matter blasting outward into empty darkness. But that picture is wrong. The Big Bang was not an explosion inside the universe. It was the early expansion of the universe itself. That is difficult to picture because every explosion we know happens somewhere. A bomb explodes in air, a star explodes in space, a fireball expands into the area around it. But the Big Bang was different. Space was not the empty stage around the event. Space was part of the event. Everything we now call the observable universe, its matter, radiation, galaxies, and even the distances between galaxies, traces back to an extremely hot, dense, compressed early state. Not a tiny ball sitting inside darkness. Not a point with empty space around it. A universe whose own distances were once unimaginably smaller. That is the strange part. The vast emptiness we see today was not waiting outside the event. It emerged as the universe expanded from an earlier state that was hotter, denser, smoother, and more compact. Then space kept expanding. As space expanded, the universe cooled. And as it cooled, particles, atoms, light, stars, galaxies, planets, and eventually life became possible. That is what the Big Bang Theory actually explains. Not why reality exists, not whether God exists, not what came before time, not the absolute first instant, but why the universe is expanding, why distant galaxies look redder, why ancient microwave radiation fills the sky, why the early universe was mostly hydrogen and helium, and why the universe has a history. So the real question is not only did the Big Bang happen, the real question is what does it actually say, and where does it stop? The theory begins with a foundational observation. The universe is not static. On the largest scales, distant galaxies are not sitting still inside a fixed cosmic container. The distances between them are increasing. Space itself is expanding. If the universe is expanding now, then in the past, the observable universe must have been smaller, hotter, and denser. Run the cosmic film backward, and today's galaxies trace back toward matter that was once closer together. Radiation becomes hotter, matter becomes more compressed. The cold, dark, structured universe we see today becomes an extremely hot, early state filled with radiation, particles, and energy. This is the heart of the Big Bang model. It does not begin by saying something exploded from nothing. It begins by saying the universe was once hot and dense and has been expanding and cooling ever since. Cooling is what allowed the universe to change. At first, it was too hot for atoms. Matter and radiation were locked together in dense plasma. Light could not travel freely. The universe glowed, but it was opaque. Then space expanded. The temperature fell. Light nuclei formed. Much later, electrons joined with nuclei to form neutral atoms. Light finally escaped. The universe became transparent. After that came darkness. Then the first stars, the first galaxies, clusters, filaments, and voids. Eventually, planets, chemistry, and life. So the Big Bang is not just a moment. It is a sequence. Expansion, cooling, formation, structure, history. And the evidence for that sequence is still visible in light, in radiation, in chemistry, and in the shape of the universe itself. But the first clue is easy to misunderstand. It is written into light itself. When people hear that the universe is expanding, they often imagine galaxies flying away from one point, as if Earth were near the center, as if everything were rushing outwards from a cosmic blast. But expansion is not galaxies moving through space from a central explosion. It is the stretching of space between galaxies. A better image is not a bomb. It is a grid whose scale changes over time. As space expands, distant galaxies become farther apart, and the light traveling through that space stretches too. When light wavelengths stretch, they shift toward the red end of the spectrum. This is cosmological redshift. The farther away galaxies are, the more their light has been stretched. That is one of the strongest signs that the universe itself has been expanding. But it does not mean Earth is special. In a broadly expanding universe, every distant observer would see faraway galaxies receding on large scales. Not because that observer is central, but because space expands everywhere. The early hot, dense universe was not over there. It included the region that became here too. Everywhere we look is part of the aftermath, but redshift is only the first pillar. The second clue is older. It comes from when the universe first became transparent. If the Big Bang model is right, something from the hot early universe should still remain. And it does. Not a visible fireball, not a photograph of the first instant. Faint radiation spread across the entire sky. The cosmic microwave background. In the early universe, matter and radiation were packed tightly together. Free electrons scattered light again and again, so photons could not travel freely. The universe glowed, but it was not transparent. Then the universe expanded and cooled. Electrons joined with nuclei to form neutral atoms. Light was released. Photons could finally travel across space. That ancient light is still traveling, but billions of years of expansion have stretched it into microwave radiation. This is the cosmic microwave background, a faint afterglow covering the sky in every direction. But it is not light from time zero. It is not the Big Bang itself. It comes from a later stage, when the universe was about 380,000 years old. Think of it as a fossil imprint, not a photograph of creation, a fossil of the young universe. And that fossil carries two messages. First, smoothness. The early universe was almost the same temperature in every direction. Second, variation. Tiny hotter and colder patches were already there. Those tiny variations mattered. Gravity amplified them across cosmic time. Small early differences grew into galaxies, clusters, filaments, and voids. So the microwave background is not just a relic. It is a bridge from the hot early universe to the structured universe we see now. But there is another clue, even more physical. Not ancient light. The first elements. The Big Bang explains why the early universe was made mostly of hydrogen and helium. In the first minutes, the universe was hot and dense enough for nuclear reactions. Protons and neutrons could combine, and light atomic nuclei could form. But the universe was expanding and cooling quickly. There was only a short window. That window is called Big Bang nucleosynthesis. It did not produce a random mixture of elements. It produced a pattern, mostly hydrogen, a substantial amount of helium, and small traces of deuterium, helium-3, and lithium. The Big Bang did not create the whole periodic table. It did not make most of the carbon in our bodies, the oxygen we breathe, or the iron in planets. Those heavier elements were forged later, inside stars and stellar explosions. So the first light elements are not just chemistry, they are evidence, a memory of a universe dense enough for nuclear reactions, hot enough for fusion, and cooling too fast to build heavy complexity. Now the pattern becomes visible. Expansion points to a hotter past. Ancient radiation points to a transparent young universe. The first elements point to early nuclear reactions. Different clues, the same cosmic history. But the universe today is not smooth and simple. It has galaxies, clusters, filaments, voids, stars, planets, and structure. So how did a nearly smooth early universe become this? The answer begins with imperfection. The early universe was almost smooth, not perfectly smooth, almost smooth. That difference matters. If the universe had been perfectly uniform, gravity would have had nothing to amplify. No denser regions, no seeds of galaxies, no cosmic web. But tiny irregularities existed. Small differences in density, small differences in temperature. Over time, gravity worked on them. Denser regions pulled in more matter. Dark matter helped build the gravitational scaffolding. Gas gathered, the first stars ignited. Galaxies formed. Clusters connected into filaments. Between those filaments, enormous voids opened. This is the cosmic web. The microwave background is the seed map. The galaxies are the grown forest. So by this point, the Big Bang theory has explained something enormous: expansion. ancient radiation, the first light elements, and the growth of cosmic structure. That is why it is not just a guess, it is a model supported by different evidence streams that point toward the same history. But now, the question changes, because a theory can be powerful and still have a boundary. The Big Bang tells us how the observable universe developed from an early, hot, dense, nearly uniform state. But it does not explain why there is something rather than nothing. It does not explain why the laws of physics exist. It does not identify the final nature of dark matter. It does not identify the final nature of dark energy. It does not prove God. It does not disprove God. It does not tell us whether reality is finally physical, mental, divine, informational, conscious, or something deeper. Those are different layers of the map. The Big Bang is a scientific model of cosmic evolution. Its limit does not make it weak. It makes it precise. A good scientific theory does not have to answer every question. It has to answer the questions it is built to answer. And the Big Bang answers many of them. But when we push it all the way back, the model reaches the edge of known physics. Run the expansion backward, and everything becomes hotter, denser, and more compressed. Eventually, the equations point toward an extreme boundary where our current physics stops giving a complete picture. This is often called the singularity. But that word can mislead. It can sound like science has proven that the universe began as an infinitely tiny dot sitting inside darkness. That is not the careful meaning. In physics, a singularity often means the theory has reached its own limit. The equations are telling us that we cannot keep using the same model here. Classical general relativity describes gravity, space-time, and cosmic expansion extremely well. Quantum physics describes matter and energy at tiny scales extremely well. But at the earliest boundary, both are needed together. Gravity is extreme. Quantum effects cannot be ignored, and we do not yet have a confirmed theory that fully unites them. So the first instant remains uncertain. The singularity may not be a physical object that really existed. It may be a warning sign, a signal that known physics has reached the edge of its map. And beyond that edge, new theories begin. Maybe there was a quantum beginning. Maybe there was a bounce from an earlier universe. Maybe time itself changes meaning. Maybe there was no ordinary before at all. But those are not the basic Big Bang. They are later attempts to explain the boundary, where the model becomes incomplete. One of the most important is inflation. Inflation asks why the early universe was so smooth, so flat, and so uniform. It proposes that, extremely early in cosmic history, the universe underwent a brief period of accelerated expansion, not ordinary expansion, a much faster stretching of space itself. In this picture, a tiny early region could expand enormously, smoothing the universe and stretching tiny quantum fluctuations into the seeds of cosmic structure. Inflation does not replace the Big Bang. It tries to explain why the early Big Bang universe had the conditions it did. But inflation is not settled in every detail. What drove it? How did it begin? How did it end? Those questions remain open. The hot Big Bang model is strongly supported by evidence. Inflation is a major extension that tries to explain the strange conditions at the beginning of that model. And this leads to the question everyone asks: did the Big Bang begin time? The honest answer is, not by itself. In some versions of cosmology, time as we know it begins with the Big Bang. If that is true, asking what happened before may be like asking what is north of the North Pole. The words make sense, but the direction may not exist inside the model. No earlier moment, no waiting room before time, no empty clock ticking before the universe appeared. But other models suggest the Big Bang was not the absolute beginning. It may have been a transition, a bounce from an earlier contracting universe, a quantum gravitational phase, or one region inside a much larger cosmic structure. The Big Bang theory itself does not decide between these options. It tells us the observable universe was once hot and dense. It tells us space expanded. It tells us the universe cooled and formed structure. But whether that early state was the beginning of time itself or only the earliest phase our physics can trace remains open. The same caution applies to another famous phrase: creation from nothing. Absolute nothing would mean no space, no time, no laws, no fields, no energy, no potential, no reality of any kind. But in physics, nothing is often used differently. Sometimes it means no ordinary matter. Sometimes it means a quantum vacuum. Sometimes it means no classical space-time. Those are not the same thing. A quantum vacuum is not absolute nothing. A physical law is not nothing. A field is not nothing. A possible state is not nothing. So when someone says the Big Bang means the universe came from nothing, the first question should be, what kind of nothing? The Big Bang theory itself does not answer that. It begins with the observable universe in an early hot, dense state, then describes how that universe expanded, cooled, and formed structure. That is extraordinary. But it is not the same as explaining why there is reality at all. This is where metaphysical frameworks relate to the Big Bang, but only from the outside. The Big Bang theory itself does not require any single metaphysical interpretation. A physicalist may see it as the early evolution of a physical universe governed by impersonal laws. A theist may see it as compatible with creation, but the theory does not prove divine creation. A pantheist or panentheist may see the expanding universe as the unfolding of a divine or sacred reality. An idealist or consciousness-first thinker may see it as space-time appearing within a more fundamental mind-like reality. An information-based framework may see it as the unfolding of structure, order, or relation. But all of these are interpretations of what the Big Bang means, and they are not part of the theory itself. The Big Bang explains the universe's early physical evolution. It explains that the observable universe has a history, a hotter past, a denser past, a smoother past, a time before stars, galaxies, planets, chemistry, or life. It explains why distant galaxies are generally receding, why their light is stretched toward red, why microwave radiation fills the sky, why the early universe produced mostly hydrogen and helium, and how tiny early irregularities became the cosmic web. But it also has a boundary. It does not explain why there is something rather than nothing. It does not explain why the laws of physics exist. It does not identify the final nature of dark matter or dark energy. It does not prove what happened before the earliest traceable state. It does not tell us whether time truly began. And it does not settle what kind of reality the universe ultimately is. That is why the Big Bang is both powerful and unfinished. It is not just a guess. It is not a final answer. It is the first great scientific model in the origin map, strong enough to explain the visible history of the universe, and limited enough to point beyond itself. Because once we understand what the Big Bang actually says, the next question becomes sharper. If the early universe was so hot, dense, smooth, and uniform, why was it like that in the first place? That is where later scientific theories begin. One of the most important is inflation, the idea that extremely early in cosmic history, space may have expanded faster than ordinary imagination can hold.